Hello everyone, this is Mr. Kozlowski and welcome to Unit 5 on waves, and we are getting into Learning Target 3, and Learning Target 3 deals with wave interactions. Students must be able to define and explain and give examples of the following: reflection, refraction, interference, diffraction, and resonance. And you must apply their knowledge to explain these interactions in terms of water, light, and sound waves. And again, I just want to re-emphasize this unit is more vocabulary intensive than what you're necessarily used to. So early on we talked about wavelength, frequency, and amplitude, and knowing those definitions. For these wave interactions, you're definitely going to have to know their definitions and be able to apply those definitions to new situations to be successful. So what are the different wave interactions that we have? The first one is called reflection, and basically reflection is when a wave bounces off a surface. And in science we actually have the law of reflection, which states that the angle of incidence is equal to the angle of reflection. And if you look to the right here, you kind of have this law outlined in this diagram. And what you have here is an incident ray, basically the ray that starts, or the ray or light wave that is reflected by this barrier. Well, we call that the angle at which it hits that barrier, the angle of incidence. Well, in the law of reflection, the angle of reflection is always equal to that angle of incidence. So if we hit it at this angle, let's say this is a 45-degree angle, it's going to bounce back and reflect off of that barrier at a 45-degree angle. If you think of like the game of pool, you play, you hit the cue ball and you bounce it off the bumper, it's going to bounce off the same angle at which you bounced that ball off the bumper. So that law is evident in all the types of waves. Reflection, examples of water waves that reflect. Ripples are basically reflections, or disturbances that basically cause when the water is reflected. Waves hitting the shore and bouncing back, that is also reflection. In light waves, you're probably familiar with a mirror, that waves are going to reflect back off of that mirror in terms of light. And then in sound waves, you've probably heard of echoes and sonar, just those sound waves bouncing off of hard surfaces, and you hear them over and over again, repeated again because of that reflection. The next property is called refraction, and refraction is the bending of a wave caused by a change in its speed as it moves from one medium to another. The greater the change in speed, the more the waves bend, and this generally will affect the wavelengths of the wave that we're talking about. So it generally bends the wavelengths. So if we look here at the wave drawing, we have the original wave. Let's say this line represents the original wave, and let's say it's just traveling through air. Okay, that's the first medium, and then it hits water. Well, in this case, when you have one wave going from one medium to the next, you're going to have that wave that is bent, and because of that, we call that refraction. Classic examples of this, examples in water. You can see that this is evidence of refraction right here, and it looks like the person's head is removed from this person's body, but it's not the case because the light waves are being refracted from what you see in the air to the water, and then actually there's probably some glass here as well. So there's actually three mediums in play here. If you think about fishing, sometimes I go bow fishing in the summer, and when you aim your arrow at the fish, sometimes you have to aim below the fish because the light front that you see of the fish is being refracted. There's always the straw and a glass example. If you take a straw that's placed into a glass, take a look at it from the side. You'll see that it's similar to this picture. There's a break in the straw but in reality it's just the light waves that are being refracted. Other examples in light waves, a prism. So here's a prism here, a laser beam being refracted. As you can see, it bends through that piece of glass. And then also sound waves can be refracted. If you look at the sound path between lightning and thunder, they're refracted due to the curvature of the earth as well as the distance they have to travel. So that is going to be refraction. Diffraction is when an object causes a wave to change direction and bend around it. No parts of the wave are affected at this time. So a lot of times we represent diffraction with wave drawings that are going through a barrier, or around it, and they simply just change direction and bend. So in this case, you can kind of see the waves of how they bend in this picture. If we look at this example in a seawall here, we got water coming through. Those waves will be bent and change direction. They're going straight, and then you can kind of see the ripples and the waves moving out in this direction. Light waves, when you see a sunset, why does the sun change colors and have these reds and oranges compared to what it is during the day? Well, it's simply because the light is being diffracted through the atmosphere. And then this is why you can hear people talking in the other room. So if you kind of look, juicy gossip going on next door versus sound waves traveling out of the door, into the hallway and into another door, those sound waves bend around those barriers. So that is the property of diffraction. Interference, there's two types of interference we want to talk about. The first type is called constructive interference. And this is when two waves overlap, arriving at the same place at the same time to add together. It affects generally the amplitude of waves. So if we look at this picture here, we have the before interference interaction. So we have wave 1 and wave 2. When they meet at the same place at the same time, they're going to be constructive, and they mean they get bigger in terms of the amplitude. So the amplitude is increased. So as you can see, when they overlap at the same place at the same time, you're going to have a larger amplitude. That is constructive interference. Examples in water waves, obviously if you threw two stones or into the water and or in this case, two fishing poles or fishing lures drop into the water, there's going to cause ripples. And what will happen is the waves will change. When they can interfere in a constructive manner, those waves actually get larger in terms of their amplitude. A big one with sound waves is at concerts. There will be spots of constructive interference where those sound waves will actually, the volume of the sound will be louder compared to another place that you may be located in a concert. And then in light waves, when you see constructive interference, you're going to kind of get this I don't want to say spectrum of colors when light waves interfere. And depending on what color it is and how it looks, will tell you constructive interference or destructive interference, which I'll talk about next. But in reality, just know that this is kind of the effect of interference with light waves. You have destructive interference. Destructive is the opposite of a constructive interference, and it's basically when two waves do not overlap, and in this case crest meets a trough, or causes the wave, it basically causes the wave to subtract from each other, and again it's affecting amplitude. So in this case it's very similar in the wave drawing, wave 1 versus wave 2. It's going to cause a third wave to decrease the amplitude in this case when they constructively interfere in this picture. Or excuse me, destructively interfere. Examples in water waves, well in this case the amplitude would decrease and the waves would actually flatten out. At a concert, there's actually also spots that we call dead spots where the sound may appear muffled because there's destructive interference. And then again, similar to light waves, you're going to see this different spectrum of colors with the wavelengths of light because they are constructively and destructively interfering at the same time. Finally, resonance. Resonance is the ability of an object to vibrate by absorbing energy at its natural frequency. So this happens a lot mainly with sound waves. And if we look at this example right here, this is a picture of air columns going through basically an open-ended tube. And if you think about it, you ever blown on a glass bottle and kind of made a sound with it, that's essentially what's going on here. And those air columns basically vibrate at different, what we call frequencies, and the wavelengths change. So as you can see here, here's one wavelength or one frequency, here's a second one, and it says a wavelength and a half, and you can kind of see the different waves. And what happens is when you match those frequencies, it will cause that object to vibrate at its natural frequency if it's matched. So here's an example of shaking a metal rod, forcing the air column inside to vibrate at the same frequency. You're going to hear that sound, that hum, that doo, right? Well, that's resonance occurring, and generally happens in sound waves. You've probably tried over here the trick where you have a glass and you put some water on your fingertip and you rub your finger. And if you rub your finger at a specific rate, you're going to match the frequency of the glass and cause a sound to be produced. That's resonance. Tuning forks. In this example, you could hit one tuning fork, and if it's at the same frequency, it's going to cause the second tuning fork to vibrate without even touching it. And then another example of resonance would be, you probably heard the opera singers hitting a high note or a high-pitched note and matching the frequency of glass. Well, what happens is that will cause the glass to vibrate so much, produce some sound, and then cause the glass to break. There's that example of resonance as well. We will discuss resonance more later on in class when we get to our sound demos later on. So to review quickly, basically what you need to know is you need to know the definitions of each wave interaction. You need to know the behavior of each wave during that interaction. And then you need to describe common examples of wave interactions in terms of water, light, and sound waves. So basically applying those definitions to new situations. So that's basically it for wave interactions. We will practice this more in detail through a series of demos and lab experiments coming up here. If you have any questions, please let me know. Also, make sure that you complete the quiz for this learning target. Thanks.